Hi, everybody. Thanks for tuning in to the fourth and final video in the series discussing how to simulate solute transfer in the BioRT-HBV model. I'm Liz, and in this video, we'll be discussing how modifying BioRT parameters affect the results of the simulations, and we'll go through how to make these modifications. So we are going to start. One of the things that we can modify are the different soil properties. In the simulation, because we don't have any reaction, we really have the soil parameters that we can modify and perhaps the precipitation chemistry. You could change how you inject the chloride or how the chloride gets introduced to the system, or you could even change the hydrology and then rerun the HBV light model. But we're going to focus on changing soil properties. So we have our soil.txt file here. And in the original simulation, we had an upper zone passive storage of 50 millimeters. Let's go ahead and double the passive water storage in the upper zone and see what effect that has. So let's go ahead and run BioRT-HBV. So we're in our folder with our BioRT-HBV. Let's go ahead and look. We want to go to our input. And I've already created this folder. So we're going to change to the sleeper chloride passive upper zone. And so looking at that, we're going to go, I'm using VI, which is just going to be a text editor within terminal, but you could just do this in TextEdit on your computer. That's a perfectly fine way to do this. So we're going to look at the soil.txt, and you can see I've actually already changed this parameter because the upper zone is already at 100. So I already doubled it from 50 to 100. And so once we've changed this parameter, we can exit out of that. And we're going to go back. We need to go back to our main folder to run this. So we have to go back to home and then HBV. And to run, again, it's .-BioRT. And this input is sleeper_CL passive_UZ. So here again, it did all of the work for us. And most importantly, it tells us that the simulation started, it succeeded, the numerical experiment started, and then the numerical experiment succeeded. So let's go ahead and look at some of the results of that. So in this, we have a plot now of the chloride concentrations in the different zones, with chloride concentrations on the y-axis and time on the x-axis. And again, this was run for 10 years, but I've only presented 5 years of data. And you can see the base case, which was the one we ran in the last video, is plotted as black in all of the different zones. And then we have a lighter color representing our changed model where we've increased the upper zone storage, and it's labeled as such. So if we look at the stream chemistry, the black and the light gray lines are pretty close to each other. There's not a lot of difference between the stream chloride when we've changed this upper zone storage. If we look at the upper zone chloride, we see that it's initially the same, but then we have higher chloride concentrations in the upper zone contribution to the stream for approximately the first 1.5 years, as noted by this higher pink line above the black. And then after about 1.5 years, it makes very little difference except for in the highest the highest concentration times in the base case. In the deep zone, you can see that we have a higher chloride concentration only from about year 1.5 to year 3. Initially, we don't have a lot of change, and then it goes back to, again, at the end, not a lot of change between the chloride concentrations in the lower zone based on how we've changed the upper zone storage. And so you can go ahead and think about what that might mean and what it explains to us. Now, that was one thing that we could modify. What if we go back and instead, let's put the upper zone storage back to its initial value and then change let's double the passive water zone storage in the lower zone. And so again, we'll modify our soil.txt file to have the WS passive LZ to be 1,000 instead of 500. So we're going to go ahead and run that. And so instead of changing into the files this time, I'm going to just VI from here, input, I believe I've called this folder, sleeper. Oops. I've called this folder sleeper chloride passive LZ, and it's going to be the soil.txt that I want to look at. So now, let's change that back. We have, again, you can see that I've already done it here. We had a passive storage of 500 in the initial simulation, and now it's up to 1,000. So let's go ahead and exit out of here. And we can just run, because we didn't change where we were in the simulation, or sorry, in the file structure, we can just run BioRT because we're in that home folder where it exists. And then we give it the sleeper CL underscore passive underscore LZ. That's the watersheds folder name. And you can see that it started the simulation, it succeeded with the warm-up, it started the numerical experiment, and it succeeded with the numerical experiment. So let's go ahead and look at the output of that. So, oops, we have the results from the simulation, again, where we have presented stream chloride concentrations in the topmost panel, the upper zone chloride concentrations in the middle panel, and the lower zone chloride concentrations in lowest panel. And again, base case is represented by dark black, and we have our simulation, our numerical experiment, as the brighter color here, or the lighter color rather. So we have gray for the stream, hot pink for the upper zone, and sort of a salmon color for the lower zone. And you can see now that this has a much bigger effect on the stream chemistry than the last simulation did. And so we modified our passive storage in the lower zone. Why do you think this is having a bigger impact? Perhaps it has to do with the fact that this is a groundwater or a deep zone dominated flow system. You can decide that for yourself. Now, if we look at the upper zone chloride concentrations, we see only a bright pink line. And that just tells us that the black line is exactly underneath that bright pink line. There's been no change between the base case and the simulation where we changed the storage in the lower zone, and that has had no impact on the upper zone chloride concentrations. Again, think about why that might be based on what we changed. Now, if we look at the lower zone storage, the lower zone chloride concentration in the simulation where we changed the storage in the lower zone, we actually see quite a big impact. We have lower concentrations of chloride in the fluid leaving the lower zone initially for about the first year and a half of the simulation. And then after a year and a half, the chloride concentration in the deep zone outflow is higher than our base case. And it actually stays high for quite a long time. In the last set of simulations, I was showing you just in the last set of results, I was showing you only 5 years. Here we've got 10 years of data, which is the full length of the simulation. And we haven't quite returned to the point where the black and the salmon colored lines are exactly the same through the whole year. And so this tells us that there's been no complete return to baseline after 10 years of simulation. And that's just something to think about, how these different parameters that you can change modify the results, and what that tells you about the watershed structure and how the fluid and this non-reactive solute move through the system. So these are just two of the changes that you could make with BioRT. There are many more that you could do. You could change how you introduce the chloride. Perhaps you want to have several pulses, or maybe you have an extended pulse. Or you could go back and you could change the HBV inputs so that you could change the hydrology and see what effect that has on solute transport. I recommend you go ahead and dig in with changing different parameters and seeing how things turn out. So thanks for tuning in to the videos for solute transport in HBV BioRT. And we will see you in the next set of videos where you can do reactive transport in this model and try out different types of things like simulating carbonate weathering, silicate weathering, carbon and nitrogen processes. Thanks for tuning in. Bye.